Can somebody confirm you can hear me?
We can hear you.
Thank you. All right, before I begin, are there any questions?
I had a question.
Okay.
Did you update the worksheet lab with that extra question?
Yes,
Yes, okay, thank you.
you may need to refresh your computer screen. Um, any other questions? Let me see.
Did you by chance see my email regarding the environmental quiz retake and how it didn't require the lockdown browser?
I put that in the question that if you took the quiz, the well, you have to use it. We're using Lockdown Browser, and if you're using Lockdown Browser, you're going to get recorded. But I have not addressed any of those questions because there's so many emails I have, and I've got about 20 more to go through. I will address the questions about the quiz um, later tonight. Any other questions? All right, I have the plagiarism quiz now graded. And all I was checking really was the first question on whether you showed me your complete environment or not. All right, if there's no further questions, let's begin. So today is October 2nd, and we are supposed to be working on Chapter 2, Chemical Principles. Do you realize that there is a quiz this Saturday? It's going to be on Practice Quiz 00, covering Chapter 1, Lab 0, Lab 1, and the syllabus. And let me make sure that I updated my syllabus online. Let me look into that. Probably be easier to download it, but let me just go here and go to the last page. It might be page 11, but we'll see. Yep, it's page 11. Nope, it's page 12. I just can't read it. What was the page 11? Um, yeah, it's updated. So the practice quiz 1 is now on Saturday. It was initially on Wednesday, but I decided to do the retake of the environmental quiz on Wednesday. All right, let's come back to the syllabus. Let me see if there's anything else I need to talk about. No, we'll do lab 2 tonight for those of you in the 6:30 lab. And that's it for the syllabus. I'm going to shut it down because I've got a lot of documents open. I kept the lab documents open. All right, I have that we had talked about water being an inorganic compound containing hydrogen bonds between different water molecules, at least when water is a liquid or when water is a solid. That hydrogen bond is there between water molecules.
Thank you.
Somebody
Professor,
has the microphone on, huh?
what? We can't see your screen.
Oh, thank you. Um, Optimize it for videos. There we go. Realize that when water is a gas, the hydrogen bonds do not form between the water molecules, and that's why water is a gas. But the water molecules form in a liquid, and that's why it's a liquid, because those hydrogen bonds form and break all the time, allowing the water molecules to, I don't know, change the shape to fit the container. And if the water molecules, the hydrogen bonds are locked in place, we have solid water, in which case it is ice. And then the water does not change its shape because hydrogen bonds don't break. And we have ice, solid water. The water doesn't change to the container to fit the container. With that it does when it's liquid. All right, any question about any of that? On the planet Earth, water molecules can split apart. H2O can split apart into H plus and OH minus. Remember, H plus is a proton as well as a hydrogen ion, meaning a proton is a hydrogen ion. And then OH minus, that's a -1 charge, by the way, is the hydroxide ion. Now, this is what water does on the planet Earth. On the surface of the sun, water can be broken down into 2 hydrogen ions and an oxygen with a -2 charge. That doesn't happen on the surface of the Earth unless you put water through electrolysis, and I don't even want to talk about that. You can learn about that in chemistry. The charged molecules of water, meaning the H plus and the OH, give water some properties and allow the molecules to participate in chemical reactions. For example, that gives the water the pH. When water, H2O, breaks apart into H plus and OH minus, it gives the water a pH. Any question about any of that? Now, when water first breaks apart, the H plus ion will be equal to the OH ion, and so that water will be pH equal to 7 or 7.0, whatever. And we'll talk about the pH in just a little bit. Any question about any of that? So on the planet Earth, water normally only breaks into H2O, only breaks into H plus and OH minus. That's different than the surface of the sun, which is much hotter. The pH of water shown here, let me blow this up, shows that neutral water is pH 7, where the H plus concentration equals the OH minus concentration. That's what this symbol means, by the way, the bracket around the H plus, and then the brackets around the OH minus, meaning that this concentration of the H plus ions is equal to the concentration of the OH minus ions. And when water first breaks apart, it is pH 7 because the two are equal. However, water can quickly dissolve CO2 in the air. CO2 can then react with water. Let me see if I can show you that. CO2 can react with water, so we have H2O. I'm not going to bother making that a superscript, plus CO2 can then combine into H2CO3, which that H2CO3 can then break apart into H plus ions. Oop. Sorry, I'm having a hard time seeing my keyboard. And then plus HCO3 with a negative charge. And let me superscript that. And superscript that. That increases the H plus ions in solution. So there will be more H plus ions in solution than OH minus ions in solution because of water reacting with CO2. Any questions about any of that? Whenever there's more H plus ions in solution than OH ions in solution, we then have an acidic environment where the H plus concentration is greater than the OH minus concentration, and that's an acid. And the pH will be between 0 up to, I don't know, 6.9 or 7. And those are all acids. A urine is actually pH 6, around that. Obviously, it varies depending on the person and what they're eating. Wine and tomato juice are around pH 4, so they're more acidic. Grapefruit juice is even more acidic. It's around pH 2. Lemon juice is more acidic than grapefruit juice. It's around pH 2. Stomach acid is around pH 1.5. It depends on what you've eaten and how soon after you've eaten, meaning once your food is being digested, the stomach will produce acids. And assuming there's nothing in the stomach to buffer the acids, the pH of the stomach will drop to around pH 1.5. The most acidic thing that you know is the acid from a car battery, and that's around pH 1. Any question about any of that? If all water, meaning H2O, were to break apart into H plus and OH minus, and all the OH minuses were to disappear in the water, meaning something were to absorb them, leaving only H plus ions, then we would have pH 0. I can't think of anything that's actually pH 0, but that's what pH 0 is. Now, you can have more OH minus ions in solution than you have H plus ions in solution, and that is a base or an alkaline solution. Seawater is a little bit above pH 8, something like pH 8.2 to 8.4, I don't remember exactly, but something like that. Milk of magnesia around pH 10.5. Household ammonia around pH 11.5, and household bleach above pH 12, close to pH 12.5. And then the most alkaline thing that you know, or the most basic thing that you know, is an oven cleaner around pH 13.5. Lime water is even more basic, close to pH 14. At pH 14, all we have is OH minus in solution, and then all of the H plus ions have been absorbed by something in the water. Any question about any of that? So the pH scale ranges from 0, meaning we only have H plus ions in solution, to pH 14, meaning we only have OH minus ions in solution. And in between, we have pH 7, where the H plus ions in solution is equal to the OH minus ions in solution. Any question about the pH? All right. Organisms need to maintain a fairly constant balance of cellular acids and bases to remain healthy. This is something you were probably taught in Biology 160, homeostasis. Organisms must maintain homeostasis to stay healthy. And if they fall out of balance, meaning the acids become too great or the bases become too great, the animal will become sick and eventually die. Any question about any of that? We don't actually talk about homeostasis in microbiology, but hopefully it's a term you had in your preliminary course, which for most of you would be Biology 160. And that is why you don't die when you drink a whole bunch of soda. I once had a picture of a kid chugging, I think it was Coca-Cola. And the reason why the child doesn't die, doesn't even become sick, is because he maintains his cellular acids and bases to remain healthy. And let me show you the number one reason why we maintain our homeostasis, meaning why we retain the acids and bases, is because CO2 and bicarbonate. If you consume a lot of acids, like chug a whole bunch of Coca-Cola or something like that, this reaction can reverse. Let me see if I can do that. Oop, didn't mean to do that. Let me get out of the superscript. Paste that in. This can reverse where this goes the other way. Just copy that, put that in the other one. So you have too much acids, this reaction can go that way, when this reaction can go that way, and then you breathe out the CO2 and either breathe out the water or your body conserves the water, it doesn't matter. And that absorbs the acids. If you have too much base, meaning alkalines, oops, I missed the minus here. Didn't copy that apparently. So you're eating too much alkaline substances, and some vegetables are alkaline. What we do is we take the CO2 from the air you breathe in, make carbonic acid, which can then split to H plus and HCO3 minus, and that will increase the H plus concentration in your blood to equalize the OH minus in your blood from eating the alkaline vegetables. I can't think of anything else we commonly eat that are alkaline other than some vegetables, but there's probably some other foods which are alkaline. If anyone can offer a suggestion, go ahead. I don't know of anything. Obviously, if somebody's taking milk of magnesia is that for indigestion or diarrhea, something like that, you will neutralize it in your blood from taking the CO2 to make the acid to keep the blood pH within a normal, healthy range. Any question about any of that? This is the main buffer in the body. We do have other buffers. All right, I mentioned about the pH. The pH is actually the amount of hydrogen ions in solution. The pH literally is, meaning actually is, equal to the negative log of the concentration of the hydrogen ions in solution. Now let me talk a little bit more about pH. I shouldn't have shut down my Word document now. Come on, go back to Word. So pH of 7 equals, whoop, ah, sorry, I'm having a hard time. I thought that's right. Is that an equal sign? Maybe I can't see.
Yes.
It is an equal sign. Thank you. I'm not seeing well. It was looking like one line to me. Put on my stronger glasses. pH equal to 7. We'll go 7.0, but no biggie. Is actually equal to 1 hydrogen ion, whoop, in 1 times 10 to the 7th water molecules. Now, where's the superscript? I don't see that there. There we go. So pH equal to 7 is 1 hydrogen ion. Let's make that a superscript 2 here. In 1 times 10 to the 7th water molecules. And this is when water is at a neutral pH. At an acidic pH, let's make that above. Oop. So a pH 6 is when there's 1 hydrogen ion molecule in 10 to the 6th water molecules, or a tenfold difference in the hydrogen ion concentration between pH 6 and pH 7. pH 5 is when there is 1 hydrogen ion in, anyone have a guess? 1 times 10 to the 5th water molecules, and etc., meaning pH 4, 1 hydrogen ion and 1 times 10 to the 4th water molecules. And we get down to pH equal to 1. Let's go ahead and do that one. Actually, I should do pH equal to 0. That equals 1 hydrogen ion in 1 times 10 to the 0 water molecules. Anyone know what 1 times 10 to the 0 is? How many water molecules is that? You should know that from your math. That's 1. So that means 1 hydrogen ion per 1 water molecule is pH 0. So that means the 1 water molecule, every one has broken down into H plus and OH minus. And of course, at pH 0, all the OH minus have to be missing. And then for alkaline solutions, like pH 8, it's the same thing. You have 1 hydrogen ion per 10 to the 8th water molecules. Any question about any of this? That's the way the pH scale works. Don't ask me about 10 to the 14th. I don't know. What that's defined as, but obviously 0 works perfectly. Each water molecule splits into an H plus ion and an OH minus ion. And for pH 0, something has to absorb that OH minus ion. All right, any question about any of that? Whoops, that's the lab. Let's go back to the... Most organisms grow best around pH 7, so something between pH 6 and pH 8. Any question about any of that? All right, let's talk about acids, bases, and salts. An acid is a substance that dissociates and gives up one or more H plus ions into solution. Like if we put HCl in water, HCl will dissociate into H plus ions and chloride minus ions, and that H plus will make more hydrogen ions in solution, giving us an acid. Any question about any of that? Your textbook says a base is a substance that dissociates and gives up one or more OH minus ions. Like sodium hydroxide is a base. When it dissolves in water, it will change from sodium hydroxide to sodium plus ions in solution and OH minus ions in solution. So sodium hydroxide is a base because there will be more OH minus molecules or ions in solution than H plus ions when we put NH, sodium hydroxide, into water. Any question about any of that? Well, here's a question for you. If we have bicarbonate, like you dump sodium bicarbonate into water, the HCO3 minus will absorb the H plus ions in solution to make H2CO3, and that's carbonic acid. That will remove the H plus ions from solution so that there will be more OH ions in the solution. Will that be a base?
That sounds like it works like one.
Yeah, that is a base because there's more OH minus molecules in solution than H plus ions. So bicarbonate, like sodium bicarbonate, is a base. And I'm just warning you, your textbook doesn't discuss that, but a base is actually something that gives off OH minus or something that absorbs H plus. And sodium bicarbonate is an example of a thing or a molecule that will absorb H plus, and so sodium bicarbonate is a base. Any question about any of that? And like I said, your textbook doesn't state it, but it's wrong when he says a base only gives off OH minus, because a base can also absorb H plus ions. Any question about any of that? All right, let's move on to talking about a salt and an electrolyte. A salt is a substance that dissociates into a cation, that's a positive ion, and an anion, that's a negative ion, neither of which are H plus or OH minus. For example, sodium chloride, when it dissolves in water, I don't know why it's doing that. It should go on for to 620, so hopefully the meeting won't stop. I'll have to look at Zoom to see why it's doing that now. Anyway, sodium chloride, when it dissolves in water, dissociates into sodium ions and chloride ions. Neither of these two ions are H plus or OH minus, so sodium chloride is a salt. And I think everybody knows that because we actually call table salt or sodium chloride a salt. However, to a chemist, magnesium chloride, which would dissolve into two molecules of magnesium ions, meaning two ions of magnesium. Is that right? No, I got that wrong. It's one ion of magnesium plus two, and then two chloride ions minus one. Magnesium chloride is also a salt. Everyone clear on that? So the way a chemist discusses salt is any substance that dissociates into a cation and an anion, neither of which are H plus or OH minus. Because a salt is not a base or an acid, and if it dissociates into H plus ions, it would then be an acid. And if it dissociates into OH minus ions, it would be a base. So salt is a substance that dissociates into ions which are not H plus ions or OH minus ions. Any question about any of that? An electrolyte is a substance that dissociates into ions, which can then conduct electricity in solution. Everyone knows that salt water is an electrolyte, and that's why when you're swimming in the ocean, you should get out of the ocean when an electrical storm, meaning a storm having lightning, comes around. Because if the lightning bolt hits the ocean, the salt water will conduct that electric current and you'll get a shock, assuming the the lightning bolt hits anywhere in the vicinity of you. I don't know how close it can be, but let's say anywhere within a mile of where you are. I'm not sure how great the distance is, but it has to be, it's fairly great because salt water conducts electricity very good. On the other hand, if you're swimming in a pond with fresh water has very little ions in it, and it does not conduct electricity well. And so if the lightning strike were to hit the pond, you would not get an electric current unless the lightning were to strike right next to you or either right on you. And that's because fresh water has very few electrolytes in it, very few ions in it, and it does not conduct electricity very well. So any salt is an electrolyte because it will dissociate into ions in water. Any question about any of that? All right. Let's move on and now talk about organic compounds. We finished talking about inorganic compounds. An organic compound is much more complex molecular structure than a inorganic compound. Like here's a organic compound. Here is an organic compound, but that's one of the simplest organic compounds we have. Actually, the most simple one is methane, shown here. Let me blow this slide up. That's the simplest organic compound, methane. That's one of the simplest organic compounds. Organic compounds typically have carbon and hydrogen in them. So they always have carbon and hydrogen in them. And most of the connections are by carbon. Like all of these connections here are being held together by the carbon bonds. There are some connections which do not involve carbon, like right here. We have this, come on, mouse. We have this connection right here happening by oxygen, but most of the connections, which are all covalent chemical bonds, happen by carbon bonding to carbon. Any question about any of that? An organic compound can be drawn in a stick figure like this and like that, or it can be drawn in a ring figure like this. In the ring figure, wherever you have a carbon, you just have a point. Wherever you have two carbon bonds linked together, you put in a double bond like that carbon here, linking to that carbon there. That's two covalent chemical bonds linking these two carbons together. In a stick figure, let me see if I've got one here. Not really, but there is a carbon in a double bond to the oxygen here. So that's two bonds between the oxygen and the carbon. And here we have two bonds between this carbon and that carbon. If ever you have a point where there's not a carbon, then you have to put in the element. Let me see if I've got a picture of that. I can move on to maybe glucose. So right there, we have a point, and what's at that point isn't a carbon, so you have to put the element in there. This point right there is a carbon. Any question about the ring formula? You do not need to know the names or the structures to these symbols. I'm just showing you different organic compounds. All organic compounds contain carbon and hydrogen. If they only contain carbon and hydrogen, like these right here, maybe these right there too, we call them a hydrocarbon. And as you know, methane, ethane, propane, these can all burn. So hydrocarbons can burn. Any question about any of that? Organic compounds may contain other elements, like this one contains oxygen. A lot of hydrocarbons do contain oxygen, but not all of them do. And organic compounds can contain other elements, like this one right there. That's a phosphorus right there. It does contain not only oxygen, but also phosphorus. So other elements may be in the organic compound. So organic compounds always contain carbon and hydrogen. If they only contain carbon and hydrogen and it's a hydrocarbon, they may contain other elements like oxygen. They may contain other elements also like nitrogen, sulfur, and phosphorus. All of these elements are held together by a chemical covalent bond. Any question about any of that? Compared to an inorganic molecule, organic compounds are more complex and they're capable of more complicated biological functions. All of the carbohydrates, the nucleotides, the lipids, and then proteins are all organic compounds. Organic compounds are always held together by carbon being the main molecule holding the organic compound together. Carbon can bond to 4 other atoms, like that hydrogen, that hydrogen, that hydrogen, and that oxygen. They can be in a stick figure like that or a ring figure like that. So the carbon